All right, so we'll pick up where we were last time, and we were just about to start a new problem in the end of the lecture notes for chapter 18, and this is diffusion and reaction inside a porous catalyst particle. Now, we've started with the simplest one-dimensional version of the constitutive law for flux, which has both diffusive and convective components. You remember the flux of A is minus C dAV dXA dZ plus XA times NA plus NB. This is the constitutive equation we've used throughout this set of notes, and we will continue to use that today, but today we're going to apply it in a different fashion, and we're going to apply it in an average sense to a heterogeneous material. And this will show you an approach for how these constituent equations may be averaged over small volumes to obtain useful results for transport phenomena. Now, after this, we're going to go into a section of the chapter 19 material that is really very fundamentally based and provides more of the mathematical framework for multi-component transport, a rigorous look at how boundary conditions are developed and applied for mass transfer problems. And we will then loop back and relook at a few of these simpler problems to examine the basis of the assumptions in detail, and then use this new machinery that we're going to develop to solve more complex problems. I've found in teaching this course that if I start simply with a few lectures of theory and there's no applications of it, that it tends to look complex and it's not clear how one would use it. If I start with some applications and point out where there are approximations and things that we can't check with the analysis we're doing, and then we come back and develop the machinery that allows us to check those approximations, I think it makes the connection between the transport phenomena theory and the actual application of it quite a bit easier. So this is a topic that is widely pursued in industry, where one will often use porous particles, zeolite particles, carbon particles, other types of porous particles as a vehicle for depositing small amounts of catalyst, be it noble metal catalysts or other types of catalysts, to carry out catalytic reactions, often in the gas phase. And the reason to do this is that these small particles, like the ones that are shown here, can have surface areas up to several thousand square meters per gram. And if you think about, how large a football field is, so it's 100 yards long, and how wide is it? Somebody knows more about football should know that. We'll hazard a guess. Okay, let's say 40 yards. We'll take Bailey's, we'll take it, it's 40 yards in this class. and so by 40 yards times 100 yards long is 4,000 square yards. And then if you, 1 square yard, I think, is about, is how many square meters? That'd be pretty close, right? In round numbers. So 4,000 square yards is of order of magnitude 4,000 square meters. Some of these particles, a gram of them will have that much surface area or more in them. And so that surface area onto which catalyst may be deposited, at which surface reactions may occur. And so these types of particles provide very efficient vehicles to get a large amount of catalyst into a small volume of a reactor or a vessel. And so very typically the way the catalyst will be distributed, if you look at a blow-up of this cross-section of this catalyst particle, it will be porous. The pores need to be interconnected for components on the outside to get in and reactants or products to get out. And then they'll be distributed on the surface of these particles, sometimes in little clumps from place to place. There'll be catalyst particles or regions which are coated with catalyst. And so what we'd like to do is analyze the mass transfer into and out of one of these particles and use that as a basis together with a macroscopic balance to analyze the mass transfer inside a device like this. And so you see again this coupling of the solution to a microscopic problem to a macroscopic problem in order to predict the performance of a macroscopic device. I showed you that in detail with the Stefan tube where we solved for the concentration profile of gas in the gas phase of the tube, and then used that to predict how rapidly the weight of fluid, of liquid in that tube would change with time. And so very often in mass transfer problems, at least on large equipment, we're coupling a microscopic mass balance solution to a macroscopic mass balance, and that would be no different in this particular case. So essentially these particles will be in a reactor, and you have a gas that is flowing past them, and we're going to take a very simple case where gas A flows around this particle. Some of the gas diffuses into the particle where it undergoes a catalytic reaction into component B. B then diffuses back out of the particle into the gas phase, and that's the product that leaves the reactor. We're going to call at the edge of the particle, at the particle surface, the concentration of A and B at the edge of this particle is going to be CAR and CBR. And those will be molar concentrations. Typically in reactive systems involving gas phase transport, we're always using molar units. So one of the approaches to solving the mass transfer of A and B in this highly tortuous pathway that is given by the porous structure would be to apply the mass balances to each individual volume element inside this porous material, and to calculate in detail the transport properties of each of the components. That is often a problem that is beyond the ability to do even with fairly complex computational help because of the complex and often unknown complete structure of the interior of many of these catalyst particles. And so we take another approach, which is a one-dimensional approach to the analysis of this problem, and this is the classic approach that you would have learned in chemical kinetics for analyzing mass transfer and reaction inside a porous catalyst particle. And so we will treat for purposes of mass transfer, we will treat this catalyst particle as being a homogeneous mixture of gas and catalyst. And the way we will do that is that we will define concentrations, for example, of gas A and gas B at a point. So we'll develop expressions for concentration profiles of A and B that vary with radial position. And those concentrations will be understood to be averaged over a volume that is small relative to the catalyst particle size, but is large relative to these features that I'm circling here with the pointer. That is, that we can define a length scale that is large relative to the local structure in this catalyst particle, but small relative to the global structure. And that separation of length scales permits us to average concentration locally and predict how this average concentration would behave as a function of R. Now, there's an entire science or branch of transport science behind these sorts of averaging protocols. It's widely used in modeling of many complex chemical engineering devices like absorbers and strippers, where you have packing with fluid flowing in the interstices between the packing and so forth. And this is a very common approach to modeling those scenarios. And we'll talk a little later when we get more machinery behind us. We'll evaluate more carefully how to interpret these average concentrations and average diffusion coefficients that we're simply going to introduce today as a first look at solving this problem. And so, but the key issue is that the pores and structure of this catalyst, inside this catalyst particle, those structural features have to be small relative to the size of the catalyst particle itself for this analysis to be rationally applied. And so, with that in mind, we can write a shell balance on a thin spherical shell going from R to R plus dr inside this catalyst particle. And we can write that the flux that enters at, or the net number of moles of A that enter at time at position R minus those that leave at position R plus dr has to be essentially equal to the amount of A that is produced or consumed by chemical reaction. And in this case, we're consuming A, and so this last term will be negative. So essentially, the only way that you change the flux of A flowing between R and R plus dr is if A is consumed by chemical reaction inside that volume element. Now, we've also assumed that this is operating at steady state, and in general, this is a reasonable assumption because the time scale for these tiny catalyst particles, which would be often on the order of millimeters to a centimeter or so, the time scale for them to come to steady state is often orders of magnitude smaller than the time scale for the entire device to come to steady state. And so the particles are essentially always behaving as if they're seeing a steady state or pseudo-steady state environment around them. And so if we take our mass balance and the limit as delta R becomes small, we get the result that is shown here, where RA is the net rate of production of compound A. And here's something that I want to point out to you that is fundamentally different from what we've done before. When we looked at catalyst surfaces previously, the mass balance in the gas phase around the catalyst surface did not contain reaction terms. And that was because the reaction occurred at the catalyst surface. In this case, the reaction is also occurring at the catalyst surface, but you see a term appearing in the mass balance, averaged, if you will, that contains a reaction term. And this term appears precisely because we are averaging the concentration of A over a small region R that includes both the gas phase of the particle as well as the catalyst surface area that is inside that small region. And so even though the reaction is only occurring at the surface of the catalyst particle, we still have the appearance of a reaction term in this mass balance, and that comes about solely because we have averaged over regions that include both the gas phase as well as the particle surface. And so that points out one of the caveats of this approach. We have to be careful in the way that we interpret the values of the flux and rate of consumption of A, and so they have to be interpreted as values averaged over a small volume in the vicinity of the radial location. And as we indicated earlier, that must be smaller than the radius of the particle. but large with respect to the dimensions of the pathways and so forth inside the catalyst particle. And so that's the basic assumption that's required for this type of averaging to work. In many practical systems, this is in fact observed. So we can take our mass balance and combine it now with Fick's law, and you see this is becoming a habit. We develop a mass balance based upon the particulars of a given problem. It's written always in terms of flux. For flux, you need a constitutive equation to relate flux to concentration. That constitutive equation that we've used so far is simply Fick's law. And so we can then put the flux expression into the mass balance and solve for the concentration profile. This is the procedure we have followed on each and every problem that we've solved. This is a common way to turn the crank on these types of problems. So if we take, for example, the reaction stoichiometry being A to B, then on average at steady state, 1 mole of B has to leave the catalyst for every mole of A that enters the catalyst. You can pick whatever stoichiometry is important or reasonable for the situation of interest, and that stoichiometry will then set the steady state fluxes of these components, or the relationship between the flux of A and the flux of B. It doesn't set the value of the flux, but it does set the relationship between the flux of A and B. And I picked a particularly simple one where the flux of A and B are equal, and so there's equimolar counter diffusion, and there's no net frame of reference or so-called convection correction, and so the flux law reduces to a simple form of Fick's law. If the catalyst particle is effectively at constant temperature and pressure, then the molar concentration is also constant, and we can write this expression as minus diffusion coefficient times dCAdr. Now, I have dropped the B off the diffusion coefficient here, and that's not a typo. That's done explicitly to remind us that this flux is an average flux over a small volume at a given point R, radial position R inside that catalyst particle, and as such, that diffusion coefficient is an effective diffusion coefficient. It is not a molecular property of the gases that are diffusing into and out of that catalyst particle, because it will have contributions to it of the tortuosity and porosity of that catalyst particle. And so I write that as dA rather than DAB to remind us that it's not a material property. And so one of the things that you can see is happening that you give up in this approach is a detailed view of the concentration inside the gas phase throughout the catalyst particle. And in that gas phase, the molecular properties of diffusion and so forth do apply. It's the same. The diffusion coefficient of one species and another is not different inside the catalyst particle than outside the catalyst particle in a molecular sense. But once we apply this averaging, then those diffusion coefficients also get averaged over the structure of that catalyst particle and are no longer material properties in the way that we normally think of diffusion coefficients. So one of the pluses and minuses of this approach are, one, that it greatly simplifies the mathematics of analysis of the problem. Now, that's a plus. The minus is that you have to inject additional knowledge, or you lose knowledge about the details of the structure of the catalyst particle, the tortuosity and exact pore structure. And so those are the balances between making a problem that gets most of the physics and is easily tractable, but has some essentially empirical parameters that are often fitted to experimental data, versus having a more rigorous model that has more of the features and structures of the catalyst in it, but is much harder to solve. And so we combine, as we typically do, our flux law with our mass balance. And here I'll write the net rate of generation of A, and this is the units on this is the net rate of generation of A, say in moles per unit volume of voids plus the solid catalyst per unit time. So it has units of moles per unit time per volume. And we can write that in the typical sense. A is being consumed, and I'll assume for the just for the sake of clarity that it's being consumed by first order chemical reaction. And so the reaction rate of A on the catalyst surface is given by a reaction rate constant K times the concentration of A in the vicinity of that catalyst surface. And I need then to multiply that by another factor that relates the catalyst surface area to the volume of the catalyst plus the voids to give me the term capital R sub A, which is the rate of generation in a small volume element that contains both gas and voids. And this term A is the surface area of the catalyst per unit volume. So again, we see in these problems that involve surfaces that surface per unit volume enters the problem naturally. And we can now combine this detailed expression for the rate with our mass balance and our constitutive equation to get the differential equation for the concentration profile. And as usual, we're not interested in necessarily understanding the concentration profile in detail. We want to know how fast A is being consumed in these particles. But in the modeling, we first determine the concentration profile and then integrate that and then take the derivative of that at the surface to get the flux and go from there. So with the differential equation, we seek a solution that where the concentration of A is equal to CAR right at the boundary, and CAR will be determined by the bulk phase concentration of A surrounding that particle. It will also be dependent on the how important the boundary layer is in taking that bulk phase composition down to the composition right at the surface. So you can imagine now, for this particular picture of a catalyst inside a reactor, that there could be at least 3 layers of modeling. One would be the modeling we're doing inside the catalyst particle. That would couple to the modeling in the boundary layer surrounding the catalyst particle, which we looked at earlier. And then all of that would couple to a macroscopic balance over the entire device to predict the device performance. And very often these mass transfer problems are broken up this way into several segments based upon the physics of the problem. So let's get back to this one. We want the concentration to be CAR at R equals capital R, and we only want that the concentration of A be finite as we go to the middle of the catalyst particle. This means that the concentration profile, this average concentration profile, be symmetric about the center line of that catalyst particle. If I rewrite this differential equation in terms of a new variable f, where f is r times Ca divided by CAR. CAR is the maximum concentration of A. It's the concentration of A at the edge of the catalyst particle. So Ca over CAR is always 1 or less. This is a very old trick in converting problems that are in spherical coordinates into problems that essentially look like they're being done in planar coordinates. You take the problem in spherical coordinates, you take the dependent variable, in this case Ca, and we normalized it by CAR because as chemical engineers it's hard not to do that. We're raised to do that. And we multiply Ca by R, the radial position. And if you make that transformation in a spherical problem, it will give you a differential equation that looks like it's a solution to the problem in planar coordinates. The reason we would want to do that is because we did that flat sheet problem last time, and so this trick works as far as I know on all reasonable spherical problems. So that's a good one to remember if you're working on problems in spherical coordinates. Boundary conditions, of course, get adjusted. So that the boundary condition on F at R is capital R times CA over CAR. And the boundary condition on F at R equals 0 is that F is equal to 0. And so with those boundary conditions, we can solve the differential equation for F and then put back into that, rewrite it in terms of concentration. You can see if you multiply the left and right-hand side by lowercase r, the radial coordinate, you'll have F on this side of the equation. So that's how this equation was first solved, and now it's been written in terms of the concentration variables. And you can see again how look at this term that shows up. K times the surface per unit volume divided by the diffusion coefficient. The surface per unit volume is going to have units of inverse length. So this is going to be like K divided by D times L. We've seen that before. So that's come up in problems where the homogeneous reaction case where you have remember with the gas A diffusing down into a quiescent tank of liquid and being consumed by chemical reaction in that tank. It had also a similar structure where the reaction rate constant divided by D and the thickness of the liquid in the tank was the variable. So you see the similarity. These look like very different problems, but the mass transfer principles are in fact similar. And if we go out to the edge of this catalyst particle and calculate the molar flow rate per unit time of A, because this particle is sitting in a bed with other particles in a reactor, what we eventually want to know is we want to couple the amount of A being produced on every particle together to do a mass balance on A in the entire device. And so we can calculate the molar flow rate of A across the boundary of the particle by just calculating the flux of A as shown here. We have the concentration gradient, and so we can calculate the flux using our concentration profile, and we get this expression for the molar flow rate of A. I'm going to clean this up for you just a little bit so it swings into focus with some of our previous work. It's traditional to compare this rate of conversion of A in the catalyst particle to a term I'm going to call WAR0. And what that means is that what would be the rate of conversion of A if all of the active catalyst surface were exposed to the gas phase concentration of A, which is CAR. And so if you could take all of the catalyst surface area out of that particle and lay it out on a flat sheet with no mass transfer resistances and expose it to a concentration of CAR, the rate at which A would be consumed by chemical reaction would be given by that total surface area times the parameter A times the rate of chemical reaction. So that's essentially, that would be the maximum rate of consumption of A, if you would, if there were no diffusion limitations. And so then we take the value of the rate of conversion of A or rate of consumption of A in the catalyst particle and divide it by this maximum value, as if all of the catalyst surface were exposed to gas with concentration, the gas concentration that's outside of the catalyst particle. And that result gives us the expression that's shown here. And this you may have seen in kinetics class. This is where I first ran across it. This ratio of the actual rate of conversion of A to the maximum rate of conversion of A is often called the effectiveness factor of that catalyst particle. Why do you think that would be an appropriate name for that term? What does that suggest? It's the effectiveness factor of the catalyst particle. Rika? Yes. It shows the ratio of how much A is actually consumed to how much A getting in the particle to how much A could be consumed if all of the catalyst sites could see the external concentration of A, CAR. So essentially what's happening here is as the gas A diffuses into that catalyst particle, the concentration of A drops, it decreases. And so the rate of chemical reaction, if it's proportional locally to the concentration of A, the rate of chemical reaction decreases. So what would be the maximum value of the effectiveness? It would be 1. What about the minimum value? It would be 0. If none of the A that went into that particle reacted at all. So this is called the effectiveness factor because it gives an idea about how effective that catalyst particle is at allowing A to go into and B to come out of the particle. In other words, if eta is 1, if the effectiveness is 1, it means that those are very free-breathing catalyst particles. There's no diffusion limitations on mass transfer, or the reaction inside is very slow, so that it's never mass transfer limited. And as eta gets to be smaller than 1, what that means is that the reaction becomes diffusion limited. That is, either the diffusion is slow or the rate of reaction is fast, and so that you can you have a mismatch in rates. And the lower eta is, the more severe is the diffusion limitation on the production of A, or the consumption of A, production of B. Now, it turns out that eta depends on only one variable when you write it in dimensionless coordinates, and it's our old friend, the Thiele modulus. Look at that. It gives the, what does the Thiele modulus tell us about? Anybody remember? Yui-san, you remember what the Thiele modulus means? That's right. It tells you the relative importance in chemical reaction to diffusion in the structure of interest. And so when K is very high, when the rate of reaction is very high, or when the diffusion coefficient is low, then the Thiele modulus is high. So high Thiele modulus goes with high rates of reaction. Now, we can also calculate, one of the things that's really interesting about this, and is always very gratifying to see, is we've worked this problem out for a spherical particle. And it turns out that it's applicable way beyond spherical particles. And it turns out that if you have a non-spherical particle, say a catalyst pellet, that perhaps is in the form of a cylinder, or particles that are in the forms of cubes, zeolite particles and so forth. For non-spherical particles, these results apply as long as we interpret the radius of those non-spherical particles. The effective radius is 3 times the volume of the particle divided by the external surface area. And you should verify that this result, just for spherical particles, gives an effective radius equal to the radius of the particle. The absolute value of the conversion of A can be given by the volume of the particles times the reaction rate that would occur if all of the particle catalyst was exposed to the concentration CAR, which is the external concentration of A, times the effectiveness factor. The effectiveness factor is less than 1, and it tells you how much less the total conversion is than what it would be if you could expose all of the catalyst particles to that same concentration. And so I can write for these non-spherical particles, the effectiveness factor is shown here, and the Thiele modulus gets modified by this ratio of the volume, surface to volume ratio of the catalyst particles. And if you then plot the effectiveness factor as shown here versus the generalized Thiele modulus, the results for spherical particles, long cylindrical particles, and flat particles lie on basically the almost the same line. And you can see that as the Thiele modulus gets large, that is, as the reaction rate constant gets high or the diffusion coefficient gets low, the reaction becomes starved. The effectiveness goes down because you can't get into the internal area of that particle fast enough to react and form B and get the B out. So lower values of effectiveness factor mean that the catalyst particle is suffocating in a sense, or starving to get reactant in and product out. So are there any questions about this before we move on? Alrighty. So the next section of notes we're going to look at are, okay, I have one set up here handwritten, but this is in chapter 19. We're going to come back and now do a little bit more. What I've shown you in these first few days are really concepts that you probably knew already from undergraduate mass transfer. You may not have remembered them very well or may not have used them in a while, but these are basic pictures of some classic problems. What we will do starting from today will be to put these on a more firm theoretical foundation and show you really we'll take the course up a notch to what I would consider to be graduate level mass transfer. And I'll show you a more sophisticated way to look at many of these problems, and hopefully the idea is this expands your ability to work different classes of problems. One of the leading scholars in this area has been John Slattery, and you're taking I think your textbook is called Transport Phenomena. Well, he wrote a book called Advanced Transport Phenomena, and I'll send it around. It is not for the faint of heart mathematically, but it provides an introduction, probably the most comprehensive introduction to and treatise on advanced transport phenomena that you'll find in one place. You'll find bits and pieces of this in the scientific literature, but he's compiled a lot of it together. And so what we're going to do is look at multi-component mass transfer. And multi-component now we mean more than two, as many components as you would like. And in order to do this, we have to reformulate our fundamental picture, fundamental laws of to account for the detailed distribution of components within a system. And the picture that we're going to look at is starts with this one. We're going to consider an n-component mixture, where n can be 1, 2, 3, 5, 10, hundreds. An n-component mixture will be comprised of separate overlapping material volumes. So how many of you have been exposed to the concept of a material volume? We have a few. One? Yeah. Only one who will admit it. So, so what's a material volume? Okay, yes, it's a volume of material. It is a volume of material, and the thing that's special about a material volume is that no little hand is that if we draw a material volume around absolutely every molecule of A, where A is the little pluses here in this mixture, we draw a material volume around A. This material volume contains each and every one of the molecules of A that are in the system, and it is absolutely impermeable to A. So an A that is in the material volume never leaves. It's absolutely and completely permeable to all other components. The B's and C's can come and go as they please, but A is always inside this material volume. Now, that doesn't place a restriction on what A can do, because like permissive parents, the material volume of A is very flexible. And so as the molecules of A move or diffuse to regions outside the material volume, the shape and size of this material volume changes with time, so that it always encompasses each and every molecule of A. And there's no transport of A across the boundaries of the material volume for A. However, the other components, B, C, etc., are free to come and go as they wish in and through A's material volume. But if the A's try to move, that volume will be expanded or contracted or changed to keep all of the A's together. Likewise, we will set a material volume for each of the other components that are in the mixture. And we will do what is classically done in this field, and that is to treat this problem as a continuum problem. And what that means is that if you went to this mixture to a given point and drilled down to the molecular level, you would find that A and B cannot occupy the same space, right? That's a fundamental principle of nature. However, we can average in a small area. Now we're talking about averaging over molecular dimensions. We can average over a small area around the A and B molecules and come to essentially a locally homogeneous description of the concentration of A and B. And so we will define as point functions the concentration of A and the concentration of B and the concentration of all other components. And it is understood that those concentrations now are averaged over molecular dimensions such that they give the average of the concentration of A that you would find in a volume that is very small relative to any other dimension in the system. And it turns out that this approach applies certainly from large equipment like distillation columns all the way down to very small scale microfluidics devices. And in the catalyst particles we talked about, where the channels may be in molecular dimensions. And so the approach has there's a very wide swath of practical chemical engineering where this approach applies. But understand that that it hinges on a local averaging of concentration about in a molecular scale region to give average concentrations of A and B and all other components. Because we will talk about the composition of A and B at a point, and if you think about it strictly at a point, there could either be an A or a B, but they couldn't both be there. And the way we get around that is by averaging over very small volumes relative to the size of any other dimensions in the system, but large enough to include many molecules of A and B and so forth. And that's the point made here at the top of this page, is that we're averaging over a small region of space to get continuum values of variables like concentration. So if we consider only a material volume for species A, and I've shown it here as a VA, as a T, with A, the little pluses that are contained inside this material volume, all that we ask of A is that mass be conserved. And to me, that doesn't seem like too much to ask. And so that is all that we ask. And we ask it in this special way. First, in words. The time rate of change of the mass of A inside this material volume is equal to the net rate at which the mass of species A is produced by homogeneous chemical reaction. And we're going to put heterogeneous reaction on off to the side here for just a moment. So the time rate of change of the mass of A in this volume is equal to the net rate at which A is produced by homogeneous chemical reaction. And the word net is underlined because it reflects the possibility that in complex systems, A may be produced in some reactions and consumed in others. And so what we're interested in here is calculating, the time rate of change of the mass of A. How many grams or moles of A are in this material volume at any given time. And the way we write that mathematically is we take the mass density of A at any point, this is that continuum averaged mass density, and we just add it up or average it over the entire material volume. This integral has to be the total mass of A in that material volume. And then we take the time derivative of that, right? That's the d mass, d time. You did this as sophomores if you're in chemical engineering, at least in a perhaps simpler way, but it's exactly the same principle. And on the other side, we're going to write as R sub A, the mass of A produced per unit time, per unit volume of the mixture. Kilograms of A produced per cubic meter per second. And we're going to average that over the entire volume. And that will have to give us the net amount of A produced by chemical reaction. Now, here comes the tricky part. How many of you, they're supposed to have taught you the Reynolds transport theorem? Anybody here not familiar with that? Okay, so we're all good. So the basic idea here is that this equation by itself, this mass balance equation, is of to put it kindly, limited use. And to get something that is more useful, we have to go from this integrated form actually to a differential form in the mass balance. And the way we do that is by applying the Reynolds transport theorem to the left-hand side of this equation. Do you know why we need to do that? What does the transport theorem do for us? Do you remember, Amanda? Not exactly. Well, we would face Bailey. Okay, it's simpler than that. It's simply that if I asked you, to take out a sheet of paper right now and take the time derivative of this term, it's not just the integral of d rho A dt dv, right? Because the limits of the integral are also functions of time. And you remember that when the limits of an integral are functions of time and you need to differentiate that integral, that you need special rules. One of them is called the Leibniz rule. Remember that? All right. Well, the transport theorem is a fancy application of the Leibniz rule. Okay, for taking derivatives of integrals where the limits of integration depend upon the variable with respect to which you're taking the derivative, and that's all we need for that. And I'm just going to give you the result. I trust that you have this in your notes from previous class experiences. But the transport theorem says that the time derivative of the total mass can be written in the following way. This is how we bring that derivative inside the integral sign. We get the so-called substantial derivative of rho A with respect to t plus rho A times the divergence of the velocity of component A. And this substantial derivative does have d rho A dt, so that, if VA were not a function of time and you would take this derivative, you just get this first term here, d rho A dt times dv integrated over v. But because this volume, material volume, is a function of time, you have the appearance of these other terms that come about as a result of essentially applying the Leibniz rule, or we call it the transport theorem. And so what is this bias? Well, if we can exchange the derivative and the integral sign for this term on the left-hand side, my reaction rate term is already under the integral sign. And so if I can bring everything under the same integral sign over v sub a, then I can combine these terms. And so that's the objective here. So I convert this term on the left-hand side to this form, and then I insert it into my mass balance, and I bring the reaction rate term over to the right-hand side. So now everybody's under the same tent. It's integrated over the material volume. And then I make the following argument. I haven't told you what this material volume is. We haven't specified it. And if you thought about taking the air in this room and putting a material volume around the oxygen that's in the space between my hands, or in the oxygen that is in this bottle, or a material volume around all of the oxygen in the room, I would expect conservation of mass to apply in each of those situations, wouldn't you? I mean, it has to. And whether I have a volume that's a liter, or 1,000 liters, or a milliliter, I expect the principle of conservation of volume to apply. And so the only way that this integral can be exactly, I can guarantee that it's exactly zero for any material volume that I might choose. And I choose that based on the problem, based on the information I want to know about the problem. The only way I can guarantee that that integral is zero is if the integrand is precisely zero everywhere inside the volume. Is it right? That makes sense? And so I come from this form to the form at the bottom of the page that is the point equation for continuity of species A. You've seen this one before. Maybe? Let's go on a little further. If I use my definition of the substantial derivative that we gave up here, that's definition right out of your calculus book, and I put that in here, I can write the continuity equation in the following way. D rho A dt plus the divergence of rho A times VA is equal to RA. What does that mean? What's d rho A dt? Well, what's rho A first? It's the mass concentration of A, grams of A per cc. And so what's d rho A dt? Time rate of change of the mass of A per unit volume at a given point. What could cause the concentration of A to change at a given point in space? What could cause the concentration of oxygen to change at this point in this room? Sorry? Well, and how would that happen? Sorry? It would be a change in temperature, pressure. Let's set, come back to that in just a second, Yui-san. Let's set the temperature and pressure constant. I want to take that off the table now, just not that it's not correct or right, but I'm trying to get at a slightly different point. But you're absolutely correct. So what was that, Yui-san? Well, thank you. The oxygen could diffuse away from this point. What else could happen to it? Reaction. How would that happen? Like what? Like, for example, what might oxygen react with? Carbon. It might react with carbon. Do you have anything more specific in mind? I'm actually very glad to see that there's a lot of hesitation to answer this question, and it almost certainly reflects the success in the university and the city's decision to ban smoking at all indoor public buildings. What if I had which I don't, let's make that clear for the record, a butane lighter, and I fired it up? What would happen to the oxygen around it? Be consumed by chemical reaction, and if it was by complete chemical reaction, make CO2 and water. Somebody would have to scrub that CO2 out of the air, but that's a separate problem. So the oxygen could react, imagine, could burn, for example. How would that be captured in this mass balance? Look, there's a little term here, R sub A. It's the net rate of production of A by chemical reaction. Now, if A is being consumed, R sub A is going to be negative. R sub A would be negative if A is being consumed. And if R sub A is negative, what's happening to d rho A dt? It's going down, right? So this is the time rate of change of A at a given point, and it can increase or decrease by chemical reaction, right? What does this term represent? That one looks kind of funny. It's got that triangle. What's rho A times VA? What are the units on rho A times VA? Sorry? So units on rho A would be grams of A per cubic centimeter, for example, right? What about the units on V sub A? What is V sub A? That's the average velocity of A at a given point in space. What would be the units on that? Sorry? The units, for example, centimeters per second. And what's the product of grams per cc and centimeters per second, rho A times VA? It's the grams of A per unit area per unit time, it's mass flux. What does the divergence mean? You know, that little triangle outside of the divergence of rho A times V. What does that little triangle do to? So this is just the mass flux. What does the divergence do to that term? Is it something nasty? So Rika says it's taking the derivative with respect to the x, y, or z coordinates, and that's exactly right. Now, what if we had a problem where the transport of A was restricted to one dimension? Let's call it z. What would be the form of this expression if where rho A times VA is the mass flux? What would be the form of this term in this expression if we only had transport, there was only one way for oxygen to move, there's only one dimension in which it could move, z dimension? What would be the form of that mathematically? Do you know, Jason? Come back to the ladies. Amanda? Well, Rika started this, so I have to, what would be the form of that expression in one dimension? Times. And if I call that flux not rho A times VA Z, right? If I called it N sub A Z, then that result would be D N sub A Z dZ. Have we seen that before? You seen it? That is what we wrote down without explanation at the beginning of our discussion of chapter 18 as the mass balance in any system which is at steady state and doesn't undergo chemical reaction if it's a one-dimensional transport problem, right? Look at this. If it's at steady state, what is the value of this term? If there's no chemical reaction, what is the value of this term? 0. And then you're left with the divergence of the flux is equal to 0 in the absence of chemical reaction. And then if it's in one dimension, the divergence of the flux is d flux dz, whatever the dimension is. So this is exactly what we have been using previously. And I said the words before, steady state, no chemical reaction. Here is the more general result, now valid in 3 dimensions and fully equipped to take account of unsteady state and situations where reaction can occur. Right? This is our point mass balance in mass coordinates. Does that make sense? We're going to use this a lot, so that's why I spend a little time with it, because this is going to be our friend. And you get, it would, as much fun as it would be to go through this again for component B and C and D as long as we want. I hope you'll trust me that if you go through that same analysis for as many components as you want, you'll get an analogous expression for each of them. So this is a very general result. Now, we've done a number of problems so far working in molar coordinates, not mass coordinates. And so how do we convert this from mass to molar coordinates? So that's what I'd like to talk about next. And I would assert that probably the best way to do it is to start from the result that we just derived, and rather than restarting over with the material volume and the fundamental postulate of conservation of mass and reapplying the transport theorem again, that we recognize that the molar concentration of A is the mass concentration divided by the molecular weight. So if the mass concentration of A is in grams of A per cc of volume, and the molecular weight of A is grams of A per mole of A, then the units will on Ca are just moles of A per unit volume, meters cubed in this case. And so if the molecular weight of species A doesn't change, and there are many practical cases where that's true, not always true, but many cases where it's true, then rho sub A is just C sub A times M sub A, and so I can replace rho sub A with C sub A times M sub A. I can replace rho sub A with C sub A times M sub A here, and it will give me a factor of the molecular weight of A outside of this term with C sub A's inside, and then I just divide through by the molecular weight of A to get the box result that's shown here. And I'll call little RA divided by MA, I'll call that capital R sub A. And that is going to be the net molar rate of reaction of A, net number of moles of A produced per unit time per unit volume. And so I have now this continuity, I'll call it a species continuity equation, right? It's continuity meaning that it enforces the conservation of mass. The species means that it's good for one species. So it's the species continuity equation. I have one of those for every component in the mixture. So I can solve these problems either in mass basis or on a molar concentration basis. The density of a multi-component mixture is defined rigorously as the sum of the concentrations of each of the components. The grams of each component per unit volume added up over all of the n components gives you the total mass density. The mass average velocity, you'll recall, is defined basically as the mass fraction times the velocity, the average velocity of each component at a local point. So I can define the average velocity in this way, and the mass fraction is just the mass concentration of A divided by the total concentration. If we wrote down the species continuity equation and we added it up over all of the components in our mixture, and let's say the mixture has n components in this case, I would add d rho A dt over all of the components, and I would add up the sums of the divergences of the fluxes over all of the components, and I would add up these reaction rates over all of the components. And these reaction rates are the net rate of production of A on a mass basis. So the grams of A, the net number of grams of A produced by chemical reaction per unit volume per unit time. And if you think about it, in mass coordinates, if I add up the net, if I have just a binary mixture of A and B, if the number of grams of A in that mixture decreases over time, and it's in a closed container, and it decreases due to chemical reaction, what happens to the number of grams of B? It increases. By how much? It increases by exactly the same amount as the number of grams of A decrease. In other words, for mass to be conserved, these reaction rates over all the components have to sum to zero. You know, because we don't create, at least in this classroom, we're not going to create or destroy matter. I won't have it. And so, if that is the case, then the sum of these reaction rates on a mass basis have to add up to zero. I can interchange the derivatives and the summations here with no problems. The summation of all the mass concentration is just the total mass density. And I can do the same thing here. And based upon my definition of average velocity, I can replace the sum over all of the fluxes with rho, the total mass density times the average velocity, the center mass of the entire system. Does this result look familiar? What is it? Where have you seen this before? Fluid mechanics. Seen it in fluid mechanics. Where? It's the continuity equation from fluid mechanics. So here we've derived it starting from the principle of conservation of mass of a single species and then combining that over multiple species. So you see the first intersection of what you might have learned in fluid mechanics class and what you're learning in mass transfer are no different. These go together like a horse and buggy, essentially. You can't separate one from the other. Now, if we perform the same operation on the molar species continuity equation, we get a different result. And we get a different result because if we add up these reactive terms on the right-hand side, this is now not the number of the mass of A, net mass of A produced per time per unit volume. This is the net number of moles of A produced per volume per unit time. And you'll recall that mass may be conserved, but moles are not, right? If you have a two-component system, A and B, and A disintegrates into 10B, as that reaction proceeds, the number of moles in the system explodes, right? And so while the sum of these terms on a mass basis has to add up to zero, they will not necessarily sum to zero on a molar basis. In some cases, if you have one molecule of A converts itself to one molecule of B, then in that case they would, but that's a fortuitous example. Very often the stoichiometry will not be one-to-one, and so the number of moles in the system will not be conserved. So when we add up all of the species continuity equations to get our overall continuity equation, we have to be mindful that that's a possibility. And again, we can define the average molar concentration as the total molar concentration as the sum of the molar concentrations of each of the components. The molar average velocity is defined as 1 over the total molar concentration times the velocity of each component weighted by its concentration on a molar basis. Ca divided by C, moles of A per unit volume divided by the total moles per unit volume is just the mole fraction of component A. And so this molar average velocity is the velocity of each component weighted by its mole fraction. And so we can develop the analog to this expression down here on a molar basis. And it looks very similar, except you have C's instead of rho's. You have a different average velocity, a molar average velocity versus a mass average velocity weighted by mass fraction. And you have this reaction term, which did not appear in the mass conservation of mass equation. Now, this is all that we need in terms of overall mass balances. We have the mass balance for an individual species, as many of them as we want. We have the mass balance for all of the species together in both mass coordinates and molar coordinates. And that's basically the end of that. The next step is to, or the further step is to very carefully decide how we're going to apply boundary conditions. And I gave you some boundary conditions at the beginning of the course, and now I'm going to come back and derive those, show you where they come from. And then the fluxes that appear in these expressions, if they're driven by diffusion, we need constitutive equations for multi-component mixtures for those diffusion expressions. And that's where we run into phenomena or terms such as the Maxwell-Stefan equation and things like this for multi-component diffusion. It's also where I have shown you so far mass transport driven by simple concentration gradients. When we write more general flux expressions, we will then include other effects: electrically driven transport, transport driven by pressure diffusion, transport driven by gradients in activity. Remember, the first day of class, I showed you this movie with the drug molecules going into the artery and not into the bloodstream, and I showed you this movie of dye going into an oil phase and not